Hello dear students, this is Tamás Jávor. Welcome back to Rubber Duck Physics. We have talked about how torque causes objects to start spinning. But once they are already rotating, what keeps them moving? The answer lies in a type of energy called rotational kinetic energy. Before we dive into rotational kinetic energy, let's quickly recap kinetic energy in linear motion. We describe it using the formula kinetic energy equals 1/2 times m times v squared. This formula tells us that kinetic energy is the energy of motion, and it depends on both the mass and the speed of the object. We don't have to worry about the direction of its velocity this time. If we square it, then we have a scalar. Think of a baseball flying through the air. The faster it moves, the more energy it has, and if it's heavier, it also carries more energy. Just like a moving object has kinetic energy, a rotating object has rotational kinetic energy. This is not a new kind of energy, it's still kinetic, meaning it's the energy of motion. We can write rotational kinetic energy as E rotational equals 1/2 times I times omega squared. Here, E rotational is the kinetic energy stored in rotation, I is the moment of inertia, and omega is the angular velocity of our object. To see how this formula fits in with the units of energy, let's break it down. The units of moment of inertia, I, is kilogram meter squared. The unit of angular velocity, omega, is radians per second, and since we are squaring it, the unit becomes radians squared per second squared, or 1/second squared. When we multiply these together in the formula, 1/2 times I omega squared, we get kilogram meter squared times radians squared per second squared, or kilogram meter squared per second squared. We recognize this as the unit of joules, which tells us that rotational kinetic energy is measured in the same units as any other kinetic or other type of energy. Now let's see this in action with a real-world example. The Earth. Earth rotates about its axis once every 24 hours, and we can calculate its rotational kinetic energy using the formula. Just for the more astronomically inclined viewers, yes, we ignore the Earth's orbital motion around the Sun. And before you ask, also the rotational motion of the Milky Way galaxy and any other large-scale motion Earth is a part of. We look at it purely as if it existed and moved standalone, like those rotating table bulbs in geography classrooms. Earth is approximately a solid sphere, so its moment of inertia is I equals 2/5 times m times r squared, where m is the mass of the Earth and r is its radius. Remember that you don't have to remember this. In case you are a DP student, neither you find it in your formula booklet, but always in the exam paper for that specific shape. Let's list the known values. Mass of Earth, m, is approximately 5.97 times 10 to the power of 24 kilograms. The radius of Earth, r, is about 6.37 times 10 to the power of 6 meters. Angular velocity, omega, can be found by noting that Earth completes one full rotation, or 2 pi radians as you know, in approximately 86,400 seconds. So, omega equals 2 pi radians divided by 86,400 seconds, which is approximately 7.27 times 10 to the power of -5 radians per second. Let's calculate Earth's moment of inertia. I equals 2/5 times 5.97 times 10 to the power of 24 kilograms times 6.37 times 10 to the power of 6 meters squared. Okay, so if at any time you feel lost, just pause or even rewind the video, and of course it is helpful to follow the calculation on your own sheet of paper. We arrive to I equaling approximately 9.72 times 10 to the power of 37 kilogram meter squared. And we can now substitute I and omega into the formula for rotational kinetic energy. Are you excited for the result? Rotational kinetic energy equals 1/2 times 9.72 times 10 to the power of 37 kilogram meter squared times 7.27 times 10 to the power of -5 radians per second squared. When you do the math, the answer is approximately 2.56 times 10 to the power of 29 joules. This gives us a sense of how much energy is stored in the rotation of a massive object like Earth, even though its angular velocity is small, but the large mass and radius mean there is a huge amount of rotational kinetic energy below our feet. Once again, it's important to remember that rotational kinetic energy is still a form of kinetic energy. It's not a new kind of energy. It's just another way that motion can store energy. As any other form of energy, rotational kinetic energy can be transferred. For example, if a spinning object hits another object, it can pass on some of that energy. We also know that when we do work on an object, we can increase its kinetic energy. The same goes for rotational kinetic energy. If you apply a torque to an object, you are doing work, and that can increase the object's rotational kinetic energy. Think about pushing the well-known merry-go-round. The harder you push, meaning more torque, the faster it spins, and the more rotational kinetic energy it gains. In the absence of external torques, rotational kinetic energy is conserved, not only together with linear or translational kinetic energy, but also just in itself. This means that if nothing is slowing down the object, it will keep spinning at the same speed, just like a moving object keeps going ahead if there is no force acting on it. Think about a spinning top, for example. Once you get it going, it keeps spinning until something like friction between its tip and the surface slows it down. Now we know how rotational kinetic energy works and how it's conserved. To give you an appetizer to the next video, what do you think? What happens when an object is both rotating and moving in a straight line, which means its axis is no more a fixed one, but also moves ahead? How do the two motions combine into rolling on a surface, and what does that mean for its energy? In our next video, we'll explore rolling without slipping, where we see both linear and rotational motion working together. To sum up, rotational kinetic energy is the energy of motion of rotating objects. It's still kinetic, not a new kind of energy, and it follows the same principles. It can be increased by mechanical work, by torques, and can be transferred to other objects. And in the absence of external torques, it is conserved. I hope this video made the topic clearer. If you are looking for more guidance, I also provide online tutoring in IB/DP physics, A-level, ball boards, and AP physics. My email is listed on the Rubber Duck Physics channel description, visible from a web browser, not the smartphone app. Don't hesitate to get in touch for more details. Thank you for watching the video, and see you next time.